Thank you. I will begin. Dear Father, we thank you for this day. Thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. All right, let me get right into it. I have a few things. This is your mission 5. You can find yours in there and hand it to the next person. I also have a handout from this book, which is Complex Analysis by Stein and Shirachi? I don't know. Anyway, this is a very popular book in the Princeton Lectures and Analysis series. This is part of a 4-book series, and I think it's the second book, but I copied a proof from their page 52 because I think it's a good supplement to, well, really perhaps a replacement for the proof that I communicated so eloquently when the camera was broken the other day. But this is essentially the proof that Sam was doubting, and I will try to go through this proof here. So here we go. So what we're looking at today is isolated zeros, and hopefully analytic continuation. Although there's an in-between topic there which is even more exciting, which is, in here, extensions of complex functions. Or maybe I should say complex extensions of functions. That would be better. All right, so here's the theorem. 4.8. It says, suppose f is holomorphic on a region omega, all right, such that f vanishes on a sequence of distinct points with limit point in omega, then f is identically 0. On omega. I think this is more or less logically equivalent to the thing we were trying to prove last class. All right. The language here is a little bit different, but it's essentially the same idea. Let me draw a picture. So the omega is I believe it says domain, right? A region. What's a region? A region is right. It's related. How is it related to a domain? I think if omega is a region, right, then that means omega is a subset of a domain union with its boundary.
Wait, it's not just the domain with the boundary?
No, because a region could have kind of funny stuff. It could have like a half fuzzy edge. You could have like a fuzzy edge and a closed edge, some sort of combination of those sorts of things. So a region is a rather multifaceted object. It's got a lot of funny stuff can go on the boundary of a region.
But you can't have like isolated points or like little tendrils coming off that are like that.
Right. Yeah. You can't have hair. Right. Yeah. Something like that. So It's mostly a domain, except on the edge you could have some parts that are not, that are not fuzzy, other parts that are fuzzy. All right, so something, anyway, it's an omega, a region. And in fact, that's kind of more what we find the natural domain of, unfortunate choice of words, the domain in the sense of points where a series is defined is often a region formed as part of a disk where, that's the theorem we had the other day, is that there's a convergence disk, right, for a power series centered at some point. And then the fussy thing is the points on the edge of the disk may or may not be included. And it can be such that some of them are included, but not others. There's all kinds of wild stuff that can happen on the edge of the radius, where the radius of a convergence is attained. And so if you think about that, that's really a region. Okay. Now, so the picture here is we've got a sequence of points, right? So maybe this is the limit point, Z star, something like that, right? And then, I don't know, maybe this is Z1, Z2, Z3, Z4, Z5, and then as n goes to infinity, we get the limit point, right? So we've got this sequence of points that converges to some limit point inside omega, right? And of course, the limit point could even be on, it could be like here too, right? It could be on the edge if that part of the edge is included. That's possible. So it doesn't have to be an interior point, but there do have to be infinitely many points in the sequence which are near the limit point. All right? That's the idea here. It's an accumulation point. All right, so let's look at the proof then. Hopefully I have not foolishly copied a proof which uses other theorems in this textbook, which we do not have access to yet. I have access to it because I've got it up here. But here we go. Proof. He says, okay, so I've already mislabeled it. This is supposed to be Z naught, right? There we go. So suppose Z naught is your limit point for the sequence. And he's used W's, so I'll do that. Sequence W sub k. K equals 1 to infinity, all right? And that f of wk is equal to 0. Does that make sense to start with that? We're saying suppose that f vanishes on a sequence of distinct points with limit point in omega, all right? Oh, I think I just noticed something that I was not paying enough attention to. Distinct. My picture had that up to the limits of my resolution of dots on a whiteboard, but distinct points. But it's the function 0 on this whole function 0 along every point. And again, those are supposed to be w's. All right. He says, first we show that f is identically 0 in a small disk containing z naught. All right. So for that, we choose a disk D centered at z naught and contained in omega, and consider the power series expansion of f in that disk. So consider f of z equal to a sum n equals 0 to infinity of a sub n z minus z naught to the n, right? Now, why can I do that? We're assuming that f is holomorphic, hence analytic, right? So the power series expansion of it exists around z naught. We know from our work the other day that power series expansion will converge, right, on some disk of convergence. I'm not sure how big it is. It doesn't really matter. But, if the disk of convergence was too big, suppose it looked like this. What would we do? No problem. we just shrink it until we have a little disk inside omega, right? We can do that. So this is for z minus z naught less than some radius, let's say rho. All right. If the radius of convergence puts you outside of the region, who cares? Just shrink down. Certainly we can analyze a little disk around the limit point. And around that little disk, we have this power series expansion, right? I think we can give an easier proof than he has here, because how can we argue that f is equal to 0 on the little disk of radius rho? Yeah.
How do we know that omega exists? Because if omega is a region, you said it could contain some points on the boundary. What if the limit point is on the boundary?
Oh. Ah. You're right. Maybe my argument only works for an interior point. I was thinking what I was going to do next was say, okay, well, a sub n is given by the Taylor coefficients, right? Oh, but I don't know that either. Like, why should the function being 0 imply its derivative is 0? We don't know that. That's nonsense. I do need to use his argument. So, and it doesn't matter. Let's see here. Well, he says. Oh, limit point in. I'm wrong. Z naught cannot be on the edge. I'm wrong. Z naught has to be in the interior.
No, but he does say, he says, in other words, if the zero is a holomorphic function, f, and they connect to an open set omega like in omega. So in other words, it seems like this definition of region is connected open set.
Well, I mean, certainly a connected open set is an example of a region. I don't disagree with that sentence, but I'm not sure without. It doesn't matter what his definition of region is, does it? Oh, it does here. Well, but we could still. Anyway, whatever the definition of region is in this book, we can agree that we have to look at a point in the interior of our region for this theorem for the proof to work. We need an interior point so that my green picture makes sense. Agreed. I was wrong. We cannot put it on the boundary because exactly what Sam was saying. I cannot find a disk reliably on the boundary with which. Okay. All right. So let's get back to work here. So we have that f is expanded by this power series, and he says if f is not identically 0, then what? Then there exists m, right, in the natural numbers smallest, such that what? A sub m is not equal to 0, right? Then he says we can write f of z is equal to a sub m times z minus z naught to the m times 1 plus g of z minus z naught, where he says g of z minus z naught goes to 0 as z goes to z naught. Let's try to digest that much more here. I think this is another way of repackaging the thing that we did the untaped day, right? When we looked at how to factor out the h. I think he's essentially doing that here. if that's the smallest one, what does the expansion for f look like? So we have f of z is, what is it? It's a sub m, z minus z naught to the m, right? A sub m plus 1, z minus z naught to the m plus 1, plus, dot, 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 right? So that we can rewrite as a sub m times z minus z naught to the m times what? Times 1 plus a sub m plus 1 over a sub m, z minus z naught to the m plus, well, to the 1, right? Plus a sub m plus 2 over a sub m, z minus z naught to the 2, and so forth and so on. And this is what he calls g of z minus z naught, right? We can do that because a sub m is non-zero, right? So I can divide by, and you can see that when you multiply that out, you get what's above, hence the purple underlined expression right here. Are you guys with me on that?
So we're thinking of G as the center of the
Yep. So, and the fact that G converges, is implicit within the given convergence of f, right? We're just peeling off part of the f series in some sense. So there's no issue about whether or not G exists or not. It's part of f. And there's the expression, 1 plus that. It's also pretty clear that as z goes to z naught, that G term goes to 0, right? Because there's no constant term, right? So if we evaluate that at z naught, we just get the 0 series. So G of z naught is 0, and G is also holomorphic, hence continuous, so certainly it satisfies this basic requirement of continuity for G. Yeah. So I think we're good on this much. Let's go to the next thought here. He says, taking z equals to w sub k not equal to z naught, all right, for a sequence of points converging to z naught, we get a contradiction. Since a sub m times wk minus z naught to the m is not equal to 0, and 1 plus g of wk minus z naught is not equal to 0, yet f of wk is equal to 0. So remember, these are distinct points. That's part of it, right?
obviously f of WK. So I guess just have it.
Yeah, f of wk is assumed to be 0 to start. I guess the lingering question I have is why can't g of wk minus z naught be equal to minus 1?
Yeah, so is it because it converges, G of z minus z naught converges to 0 as you approach z naught, so you can choose
Yes, very good. So the limit as k goes to infinity of g of wk minus z naught, right, is equal to g of the limit as k goes to infinity of wk minus z naught, which is equal to g of, I guess that's g of 0, isn't it?
Right. So yeah, we already know that. But
And g of 0 is what?
0.
Oh, I'm sorry.
It is
That. Goodness gracious. That actually, I think I'm misinterpreting it. This is, sorry. Writing this already is like, maybe I should call this h of z, all right? And so really, we're thinking about h of wk, right? And the limit as k goes to infinity of that, which is h of z naught, right? Which is h of z naught minus z naught. Or g of what? Yeah, and g of 0, well, okay, so then I'm an idiot. And I'm sorry, I having some kind of mental kerfuffle. Anyway, the point is that is the 0 series, so it's 0, right? You might ask, well, why can you pass the limit as k goes to infinity inside that? That's again by the continuity of h or g, depending on which letter you want to use. But it's exactly what you said. I can't have g of wk minus z naught to be equal to minus 1 for k going to infinity, because it contradicts the fact that as k goes to infinity, this term should go to 0. You can't have values minus 1 and 0 at the same time. I mean, like it's... So then that's a contradiction, which means what? That means that f must what? So it's not identically 0, so it's identically 0, right? So there you go.
what's the last paragraph where you said we can do these factors? Up until this point, we
Oh.
assume that it's identically 0 and that it's
Yeah, let's see here. Oh, right. So sorry. Yeah, like you said, we just shown it's identically 0 on the where, on the disk D. We've shown it's identically 0 for the green disk as in my picture, right? So as you do next, he says, we conclude the proof by using the fact that omega is connected. He says, let U denote the interior of the set of points where f of z equals to 0. So it's the interior of z in the region, right, such that f of z is equal to 0. If it's an interior by construction is an open set, okay? He says use open by definition and non-empty by the argument just given. We just showed that there are points where f of z is 0, right? I mean, there's an open set. At least the set of points z such that z minus z naught is less than rho. That's an open, it's an open set on which it's 0. So at least that is included in U at a minimum, right? So it's non-empty by the argument just given. The set U is also closed. How is this? Since, here we go. If Zn is in U and Zn converges to Z, right? then f of Zn converges, by the way, to f of z. Which is equal to 0. I don't know if I've said that quite right. Let's see here. He says, then f of z equal to 0 by continuity. So I've probably not talked enough in here with you guys about the sequential way of looking at a set being closed. What does it mean for a set to be closed in terms of like sequential topology? So a set is closed if what? In terms of sequences. If each sequence of points in the set, let's say S, converges to a point in S. This is how we define closed in terms of sequences. Just to, give you a sense of, here's a, if you had, an open set fails this, right? We could take like the open disk. You could take the sequence of points on the unit disk that go from, like a half. Well, yeah, let me see. How about 1 over n, right? Oh, that's not what I want. 1 plus 1 over n. 1 minus 1 over n. I'll get it eventually. This sequence, what do I mean?
I was just wondering, because it says that, well, maybe I might be getting ahead of it.
Okay, so, the first one's here, then a half, then 2/3, then 3/4, then da-da-da-da-da-da, right? This obviously limits to 1, right? But 1 is not an element of the open disk, right? So that proves that the open disk is not closed because you have a sequence of points in the open disk which converges to a point outside of the disk. Yeah.
So is it a disk at 0 that goes out 1? Like
Yeah, I mean the usual unit disk. This is that's the disk I'm talking about. That set is not closed because there's a sequence in the set, right? Everything in the sequence is in the set, yet it converges outside the set. Right? It's not closed. In contrast, he's claiming that U is closed. He's using this sequential understanding of closed, right? So we look at a set of points Zn in U such that Zn converges to Z, all right? The goal is to show that Zn converges to a point inside U, right? What does it take to be inside U? You need to have f of z equals to 0, right?
And you need to be in the interior.
Yeah, and you also need to be an interior. So you also need to find an open disk, open set of points around that point where it's 0. That would suffice to show that it's in U.
So do we mean that it's in some way closed with respect to omega? Because it says if Zn converges to Z, then we get that Z is in U, but that's only true if the Z is in omega, or like in the interior of omega.
I have to take a sequence of points in U. I'm not sure what I haven't quite processed your question yet, Sam.
We take a sequence of points in U, and then we say it converges to Z, and then he says that like we get that Z must be in U by the argument above, but the argument only applies if the Z that it converges to is also in omega. Right.
Let's argue why it's in omega. Okay, so look at this. So this is f of Zn. My point is f is holomorphic, right? Which means it's continuous. A continuous function has the following wonderful feature, which is that this is also equal to the f of the limit as n goes to infinity of Zn, right? Now, by definition, this is Z. So this is f of z, right? But on the other hand, what do we know about f of zn? Zn is in U, right? So what is f of zn? It's 0, right? So this is the 0 sequence, which of course limits to, if you allow me this small manga style calculation, 0. So that shows you that f of z is 0. Then we can go back and use this argument again to find an open disk around that where f is identically 0.
So that argument only applies if the limit point is in omega.
Limit point
Right,
is-
so we say that as an assumption. So we're saying, assuming the limit point's in omega, then the limit point must be in U as well, right? Is that what we're saying?
Yeah. I mean, z has to be... Yes, we're looking at a sequence of points in... in principle, here's omega, right? And here's u, right? And I suppose, yeah, it could be that in principle, that z is on the edge of u or something
Yeah.
a priori before we make the argument. I mean,
But it can't be on the edge.
but it has to be inside omega, right? Yeah, so I do think you're right. I do think we need that omega is open.
So
Yeah.
when we say that U is open and U is also closed, and omega is also probably open, and like say omega is just an open disk, then we're trying to argue that U is all of omega. But if U is closed and omega is open, does that mean that U is only closed with respect to omega and not like closed with respect to the complex plane?
Oh, I don't know about all that. But what I can tell you is we've shown that the limit point of Zn, right, Zn goes to Z, is again a point in U, right? And then I think I'm going to agree with you, Sam, but I'm not. So the limit point is in U, which shows you that U is closed because we just took an arbitrary sequence in U and showed that it converged to a point in U. So that satisfies the sequential definition of closed. So we have U as both an open set and a closed set. All right? What does that mean? The other way of, so closed, the topological definition of closed is that omega complemented, well, not omega, but
Yeah.
no, it's, I mean, the complex plane minus U is open. And U is open. On the other hand, if we take omega and we intersect it with the complement of the complex plane by U, then this is the intersection of open sets, which you can prove is open. That might have been a homework for you guys. It was almost a homework if it wasn't one. So the intersection of omega and this complement is open. U is open, but you can argue that if we call this thing V, then U union V is equal to omega, where U and V are empty, intersects empty. In other words, it's a separation. I think I know what you're getting at now, Sam, but yeah. So the topologically closed means that if you take the set and you take the universe in which you're living in, which in this case is the complex plane, and you complement by that set, if it's closed, then the complement is open.
It seems like here the universe is using omega.
Well, I maybe in this book he's defined subspace topology. I don't know. That seems like a topic for next semester. Okay, so, or maybe after class. All right, anyway, finally, we have it then that if the function is identically 0 on a sequence of distinct points with a limit point in the set, then the function is identically 0. Let me I think the rest of my notes are actually pretty clear. It's just this particular proof was not quite right. And one of the real problems with the proof in the notes is I don't emphasize that. There's one point in the proof I'm like, H has to be 0. Because H is 0 at the center point, like H has to be 0 nearby. From an epsilon delta perspective, we're using the continuity of H. So there's a theorem. If you have a function which is 0 at one point, and if a complex function is 0 at one point, right, and it's a holomorphic function, which means, among other things, it's a continuous function, right? Okay, so if the function's 0, the absolute value of the function is 0, all right? And then you can argue that if it's 0 at one point and you have continuity of the absolute value of the function, it must be such that the absolute value of the function is 0 at all nearby points. You can't have the situation where you have 0 at one point and then it jumps to non-zero. Like, it has to stay close to 0 is the thing. You can use that closeness to get the result I want, I think. But this is better. It's sufficient to say that the proof in the notes is not quite right, okay? We can all agree on that. So, come on. Uh-oh, I gotta be careful. The way they got these things set up, if you pull on it wrong, you'll knock the thing over inside, and then it won't work. What happened? You what? Oh, you want me to do it? I can do it. I was going to come back and do that anyway. I try to make a habit of doing it, because when I don't do it, bad things happen. All right, so what of course I've neglected to say in class today, which I said in class to you guys last time, thank you, is we defined what? Like the order of a 0, right? And so I have some of those things in these notes. We should talk a little bit more about that now that I've gotten past the proof that I butchered, sort of. So one of my examples, we went through this example last time, but I'll just mention it again. If we look at sine of z squared, you can see that this has a 0 of order 2, because the lowest order thing that appears is z squared, and then of course everything after you can factor z squared out of. So anyway, the order of this is, the order of the 0 is a double 0. It's order 2 because we can factor the z squared out. On the other hand, we can also have a 0 at n pi, and these arguments down here show you that the derivative at plus or minus the square root of n pi is non-zero, which means that plus or minus the square root of n pi gives us a simple 0. There's an infinite family of simple zeros for this function, but there's the one double 0 at 0. Okay? Now, I thought this calculation was kind of fun, and so what I did here was to show you through explicit series calculation that you can prove that the 0 at plus or minus the square root of n pi is a simple 0 by explicit manipulation of series, if you have enough willpower and belief in your ability to calculate with series. Here it is. And this illustrates some of my bag of tricks for manipulating series. So I'm sharing with you some technical secrets. First of those secrets is to add 0. I see it. Fine. It's all right. I came prepared. Match this. Haha. There we go. Maybe one for here, one for there. No. Oh, okay. Okay, so I square that. At least be glad I didn't bring the green one. So you square that thing, and we get that squared, 2 root pi, blah, 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 plus n pi. What happens with the n pi going from here to here? Well, I used a little bit of trigonometry. If we have sine plus n pi, it's minus 1 to the n times the sine of the argument. Because if you add even multiples of pi, it just brings you back to sine. If you just add pi to sine, it brings you to minus sine. Add 3 pi to sine, it brings you to minus sine. So this is just a cute identity for adding n pi. You can pull out a minus 1 to the n, get rid of the n pi, which is ever so lovely because then this and that are at least having a z minus square root of n pi term in them. So when I plug that into the power series expansion, here's my u minus 1 over 3 factorial u cubed, right? There's always at least a z minus n pi term. And if you look at that, you can factor out this and that, and then there's a constant term and this series, which shows you explicitly that sine of z squared has a simple 0 at square root of n pi. Which do you like more? The checking the derivative is non-zero at n pi, square root of n pi, or the series calculation? Yeah, okay. Here's another one. 1 minus cosh z is, it's 0 at 0, but the derivative is also 0. But the second derivative is minus 1. So this shows you that this is a double 0, which you can, of course, also calculate directly by just subtracting the cosh series from 1, like this, and factoring out the z squared. Now, in this example, you see the contest between using the definition of the double 0 versus direct series calculation and factoring. It's kind of a wash. Which one's easier here? I mean, I don't know. I think this calculation, this subtracting the 1 off, factoring out the z squared, is not that bad, right? I should also define for you guys, is 0 at infinity. What's that mean? That means that f of g of w equals to f of 1 over w has a 0 of order n at w equal to 0. Theorem, if you have an analytic function, a 0 of order n at infinity, then you can expand the function like so. Just like if we have a 0 of order n at z naught, then we get like z minus z naught to the n plus z minus z naught to the n plus 1 and so forth with coefficients. Yeah. So here's one. 1 over 1 plus z cubed. If we look at g of w, which is 1 over that, multiply by w cubed over w cubed, you get that. Geometric series, there you go. This has a 0 of order 3 at w equal to 0. Therefore, this has a 0 of order 3 at infinity. That's the way you do it. So we got to look at expansions of 1 over z, essentially, to understand infinity. If we look at the exponential function, look at the g of w, which is f of 1 over w, e to the 1 over w, which is 1 plus 1 over w plus 1 half 1 over w squared. Yowzers. So that is not analytic at w equal to 0. All right. This is, in fact, not analytic at w equals 0. We cannot even hope to ask a question of whether or not there's a 0 at infinity for the exponential. It's outside the scope of discussion. Now, we will talk about that in the next chapter, but we can't talk about it that way. Here's another one. F of z, z minus 1 over z minus z naught to the n. And rather than looking at the g function, I just try to write it direct. So the theorem said that if you can expand the function as a sum of reciprocals, right, then that reveals directly the order of the 0 at infinity. So I'm just doing that calculation directly here. And what I do, of course, is I factor out the z to the n. And so to be fair, I divide all of this by z to the n, which then simplifies like so. And then to get from here to there, what do I do? What's this step from here to here? It's what? From this one to that one. What did I do? It is exactly that. This is the geometric series taking all of this to be the R. And that's reasonable because we're assuming that the modulus of z is very, very big, which makes that very, very small. And there you go. I factored out 1 over z to the n times something, which is 1 plus these sorts of things. That suffices to show that this function has a 0 of order n at infinity. All right. Moving along here. So, theorem, if D is a domain and f is an analytic function on D which is not identically 0, the zeros of f are isolated points, right? That's logically equivalent to what I proved today, right? In other words, today we proved that if the function has zeros along a sequence of points, which are not, they cluster up on that one limit point, then it forces the function to be 0 everywhere. So this is saying that if you have a function which is not 0 everywhere, right, then if it has zeros, they cannot bunch up. They have to be isolated. All right. Anyway, that's the proof, which is not quite right. It's not quite wrong either, though. I'm more interested in the applications of that, though. I spent enough time already, I think. If f and g are analytic on a domain D, and if they are equal for each z belonging to a set with a non-isolated point, then f of z is equal to g of z for all z in the set. So you can look at the set of points where they're equal. This is the so-called coincidence set. And if it had a suppose it had a non-isolated point, right? Then if we looked at h of z, which is the difference of these, if that h is not identically 0, then it contradicts the isolated zeros theorem. So since by definition it's a set of, C by its definition is a set of non-isolated zeros for h of z, we find that h of z is equal to f of z minus g of z, which must be identically 0. I don't know, it might be a useful exercise for us to try to go through these theorems and restate them, like try to reprove them in light of the theorem we proved today, right? It's the same technology, but kind of like glass full versus glass empty kind of thing, But anyway, I before I call yet another mulligan on this lecture, let me go on. So a related theorem is that if we have a subset, E, a subset of D that has a non-isolated point, we have a function of two variables, all right? So this is a Z and W and D, and it happens to be that this is analytic with W fixed, and it's also analytic with Z fixed. Then if we have this is equal to 0 on E, then it follows it's equal to 0 on all of D. Now, let me just try to get to the point here. What we're saying is that if you can show that a complex function is 0 on a set that has a non-isolated point. So what are sets that have non-isolated points? A line segment is such a set. An open disk is such a set, right? The picture of the sequence is such a set, right? But usually it's enough to know that this theorem applies for line segments. What it's saying is that if two complex functions are equal on a line segment, it follows that they must match on the larger domain in which that line segment is found. If you have that the two complex functions are holomorphic on a domain, if they are matching on a line segment in that domain, it follows that they are equal on the whole domain. That's what this theorem is saying. And this is also true for two variables. So for example, you could use this to do your homework problem. This is not how I want you to do it, but we know that e to the x times e to the y is equal to e to the x plus y for real x and y. Well, that's true for the whole real line, right? So by the principle of permanence of identity, we can extend that rule for x and y being complex. That would be a consequence of this theorem. I do want you to do it with the series calculation, though. So the thing I'm trying to get at, and not getting there nearly fast enough, is just this, that all of the functions we've defined in here, sine, cosine, e to the z, all these functions which are entire, they're holomorphic on the whole complex domain, because those restrict to the ordinary sine, cosine, exponential on the real line, and because that's a set that has a non-isolated point, in fact lots of them, it follows that those are the unique entire extensions of sine, cosine, the exponential to the whole complex plane. It's not really, our transitional definition isn't really transitional at all. It's what has to be. It's the only way to extend sine, cosine, exponential. So now, other things are more nuanced, like the logarithm. That's what we'll talk about next time, analytic continuation, and what that's a little bit more complicated. We'll talk about that next time. So anyway, thanks guys.